All right, so I'm from Dstillery, which is a DSP slash data science company in New York. This is about blacklisting the blacklist in digital advertising. I did the work with my colleagues Claudia Perdich and Ori Stidelman. First, I'm gonna introduce the background, and then I'm gonna talk about the bidder pipeline of our bidder, and then I'm gonna talk about the publisher marketer blacklist identification algorithm, the meaning of which will be clear in a minute. Then I'm gonna talk about out-of-time validation of the algorithm, and the performance results, the live performance result by running the algorithm in our bidder. And finally, I'm gonna talk about an exploitation balance problem. Related to this. All right, so digital advertising, we all know it's about a 50 billion, maybe this is a conservative number, industry, and there are billions of ads that are ad slots that are bought and sold every day on exchanges through real-time auctions. Buyers such as Dstillery, we bid to show an ad on a publisher or an inventory on behalf of our brands, our clients' brands or marketers. And we receive bid requests, and then we need to decide what marketer to bid for these bid requests, and we need to describe what bid price to submit. This is the job of our bidder. And all these decisions is based on the bid requests values, such as click-through rate or estimated conversion rate across multiple ad campaigns. There are a lot of papers about how to estimate a conversion rate or click-through rate using machine learning. You can do logistic regression, you can do trees. There are a lot of papers about those. This is not, my talk is not about estimating the values. It's about more about win rates. So it's commonly believed that the highest bid will win the auction in the exchange, but there are exceptions. So one example is that publishers sometimes they blacklist the marketer, for example, to avoid conflict with the direct deals. What does that mean? That means a publisher could have a deal outside of real-time bidding with some marketer. For example, if I'm New York Times, this month I have a deal with BMW, and that deal tells me I'm not allowed to show ads for Mercedes or Audi. So that would be a case where New York Times will not refuse to show an ad for for Mercedes over this month. So if I'm a buyer, if I bid for a banned marketer or a blacklisted marketer, I waste computing resources in a low latency environment, and I'll explain this in a while. And I also lose an opportunity to show a good ad for a different marketer, because when a bid request comes, I could have shown an ad for a different marketer, but instead I've shown an ad to a banned marketer, so I lose the opportunity to show a good ad for a different marketer. So we built an automated system to detect the content of the publisher blacklist and limiting bidding for banned marketers. So here is a simplified diagram of our bidder. So when the bid request comes, you first do some processing, and then we find some ad candidates. For example, a bid request, we may find, in this diagram, we may find 3 ad candidates. These are all qualified for this bid request. And then we want to determine which ad to show. So in this diagram, I have a random sample. But let's focus on the left path, which is most of the times. So we have this banned marketer filter. When the filter tells me this is about the algorithm, when the filter tells me marketer 1 seems to be in the blacklist for this publisher, so instead of bidding on marketer 1, I'm bidding on marketer 2 or 3. And in this case, marketer 2 has a higher price, so marketer 2 wins in the internal auction, and then gets sent to the bid. And on the right side, there is exploration path, which is I don't apply any filter at all. So in this case, marketer 1 will still be submitted, assuming it has the highest price among all 3 marketers. And all of this has to be done within about 100 milliseconds, actually more correctly 50 milliseconds. So that's why latency time is very important in this problem. All right, so how do we identify a banned marketer? So all of this is about win rates, which is basically the number of impressions you win divided by the number of bids you submit. Obviously, price is an important factor of the win rate, but I'm going to factor out price because this is about win rates, factors that affect win rates other than price. So when a win rate for a marketer is much lower than other marketers' win rate condition on the same exchange and same publisher, that means this marketer probably has a problem with this publisher. So this is how we identify a marketer as being blacklisted by the publisher. And as I said before, win rate is sensitive to price, so we need to correct for price effects. And how do we do that? So we first discretize our bids into price buckets and compare the actual number of impressions against the number of impressions expected from other marketers' win rates on the same exchange, same publisher. So here's the algorithm. Basically, first of all, we're gonna split these. There are a few of these notation here. E is exchange, I is inventory, P is price bucket, and number of bids, number of impressions. So basically, compute for each price bucket what is the expected number of, what is the expected win rate for any marketer by averaging over all marketers. And then we compute an expected number of impressions for a marketer that, and in a certain price bucket by multiplying number of bids and expected win rates. And then we aggregate over all price buckets to compute the expected number of impressions and the actual number of impressions. So at last, if the actual number of impressions you get is much less than the expected number of impressions you would get, assuming the win rate is the same as other marketers, and then that's a sign of this marketer could be a bad marketer. So now there's in this equation there are some parameters alpha and beta. So as you can see, this is kind of like an elementary statistical equation. This is like the variance. This is the standard deviation. This is the mean. And moreover, more than a statistical problem, this problem is more like a business problem. We want to identify marketers whose win rate is much less than other marketers on the same exchange, on the same inventory. So that's why we have this choice of alpha and beta here. In this case, the business problem tells us that the alpha should be less than 1. So in fact, we chose this set of parameters. And from this equation, it tells us you need this number to be at least 7 in order for this equation to the right-hand side to be positive. So that means you require enough data for effective detection of bad marketers. And in live, what we do is that every day we're going to refresh the list based on the last about 8 days of data and apply the filter in our bidder. 8 days of data is because we don't want this number to be too large. Because if this number is too large, then we're going to be slow to react to changes in the blacklist, because a publisher may activate a blacklist and then a marketer may be removed from blacklist, and things may change over time. So we want to react to that quickly. Therefore, this number cannot be too large. Also, this number cannot be too small because we want to have enough data. So we run the algorithm, and then we generate the blacklist based on the last 8 days of data. And now we want to do some validation based on out-of-time validation based on future data set. So what we do is we generate the list based on the last 8 days, and I'm going to call that the estimation set. In the test set, we're going to monitor win rates for exchange inventory combinations in and outside the blacklist. All right, so here is the data. As you can see in the training set, in the estimation set, if you're not in the blacklist, your win rate is pretty close to your expected win rate. But if you're in the blacklist, your win rate is much lower than the expected win rate. And also the win rate is much lower than if you are not in the blacklist. And all of those is true in the test set, because as you can see in the test set, if you are in the blacklist generated by past data, in the next day your win rate is still much lower than the expected win rate, and also your win rate when you're in the blacklist is much lower than average. So that means we're not overfitting the data, and also the changes in win rates are not too fast to render the learning ineffective. So now we put this system in our bidder. As I said before in this slide, we have a control group where we don't apply the filter, and we have a treatment group where we apply the filter. Now, all right, this is a little slow when I turn pages. All right, so one simple comparison is you compare the win rate difference between the control group where you applied, where control group is where you don't apply the filter, and the treatment, there's a mistake here, and with treatment group where you apply the filter. So when you apply the filter, the win rate is actually much higher than when you don't. Actually, you can see there's about a 24% lift on the first 2 days, and we've deployed this thing for 4 months, and on average, applying this filter gives you about 23% lift on the win rate, bidding win rate. So, and also, there's not only a significant increase in win rate, but there's also a significant reduction of system load. As I said before, system load is important because we're in a low latency computational environment. So if you don't bid on combinations in the band marketer list, you submit 20 to 30% less bids. So that's a good reduction in terms of system load. And moreover, when the filter is applied, as I said before, if you don't apply the filter, you lose opportunities to show an ad to a different marketer. So when the filter is applied, there's about a 50% chance that you can find a qualified alternative marketer to bid. So that allows this finding a different marketer to bid allows us to deliver actually 6% more impressions and making only 14% fewer bids. And finding this alternative marketer to bid is very good for alternative marketers' campaign performance because in the absence of BM filter, we lose active opportunities to show good ad to alternative filter. And this also has to do with the way that our pacing engine works. Our pacing engine activates good opportunities for each campaign. So if you lose a good opportunity, the pacing engine has to activate a worse opportunity to bid. All right. So I've talked about control group and treatment groups. Now I'm gonna talk about the last part, which is the exploitation balance. So we dedicate a fraction of bids to exploration, which is also the control group. Now the question is, how much C should we choose? What is the control group sampling rate? If your C is too large, and then you make too many bids for band marketers, which you don't want to bid. If your C is too small, then you make too little bids for some band marketer combinations, and then because you make too little bids, you cannot record their win rates in the future, and then you actually end up, because you don't have enough data to tell if your win rate is low, then you end up bidding more on them in the future. So there's an optimal control group sampling rate that minimizes the regret in the exploitation literature, or in this case, minimize the number of bids you spent on bidding with band marketers. Now this is about computing the optimal sampling rate. What we do is we compute the number of bids made every day for one band marketer as a function of the sampling rate, and then minimize respect to C to get the optimal sampling rate for one band marketer. And for different band marketers, the optimal sampling rate may be different. If we choose a single optimal sampling rate in our system, we just consider all band marketers. So and this is about, I'm first going to talk about how to compute the optimal sampling rate for one band marketer. And to detect the band marketer, you need to make at least n bits for the last T days. And n is related to the algorithm and also related to the global win rate. Because as I said before, you need to have at least seven expected impressions is in one of those previous slides for the algorithm to detect a band marketer. So n turns out to be related to that, and n turns out to be 175. So as you go through the math, I'm just going to talk about intuition first. There are three classes of band marketer combinations. A small band marketer, which means you see it very, very infrequently. They are never caught by the algorithm because you just don't see them. You rarely bid for them. There's not enough data to record their win rates. A medium-sized band marketer, it will actually be caught on some days and actually escape detection on some other days. It actually forms a cycle, a 9-day cycle if T equals 8. And for a large band marketer, you see them so much that the algorithm catches them every day. So this is about the three classes of marketers and the number of times you actually bid for them as a function of the sampling rate. So this is the equation, and x, and this is the small marketer case, large marketer case, and a medium marketer case. N is the number of bits you actually see them in the absence of, you naturally see them in absence of any filter. And for the medium marketer case, this number of times you bid is actually related to the number of days it remains in the band marketer list over a t+1 day cycle. So this is the equation, and then the equation looks like, in the previous slide, looks like this. This is the number of bits made per day versus the sampling rate for a marketer that we naturally see 150 times per day. As you can see, from the right to left, the band marketer transitions from staying in the band marketer list, being detected every day when the sampling rate is large, and then as you decrease the sampling rate, it sometimes will be not detected for 1 out of every 9 days, and if you further decrease the sampling rate, it will actually escape detection for every 2 out of 9 days. And the optimal C for this band marketer is actually around here. It's actually 2%. As you can see, the optimal C for this band marketer is not 0. So if you want to, for simplicity, we just, in our system, we have an optimal C for all band marketers. In order to compute that optimal C, we just sum over all band marketers. So we first identify all band marketers from data over a very long period of time, like 3 weeks. Then we minimize the sum of bits for all of them and compute the optimal C, which turns out to be 1%. So as I said, for simplicity, we use one single optimal C for all band marketers in our system. But this is a constraint, and it could change in the future if we decide to get more sophisticated. And that's all I have. Is there any questions?